So, what we had seen last time was how to handle situations where we made oscillations between three fields. So, we had to use all angles, theta 1, theta 1, then we use the equivalating phase delta. We know that the phase is chi, level phase is chi, and the higher order phase is phi. They don't play a role again. So we have to be only with the three angles in both phases. And then we calculated the probability of conversion, probability of UE to UE. And in principle, we can calculate fluid, EU to EU, UE to UE, So what we will do today is we will see whether whatever we have developed, the Neutrino thing, is all the restricted. So that formalism is enough to handle all situations. It turned out that there was one experiment which told us that perhaps that formalism is not enough. And we have to go for more than 3 neutrinos. So let's go through that argument and see what led us to believe that there is perhaps another neutrino more than electron more than this neutrino. That is what I call the sterile neutrino. And precise definition will come in course of this. So what we do is so I'll first tell you about so-called short baseline experiment. I will tell you what that means. LSND, which is liquid scintillator neutrino detector. It's as the name is liquid scintillator detector. That was the experiment that gave us so-called LSND anomaly, which led us to believe that there may be some extra neutrino. This anomaly meant that we have to add 4 neutrinos, which we will claim is going to be sterile neutrino. Then we'll see what we did to constrain this sterile neutrino, to see what its mass can be, to see what its mixing with normal neutrinos can be. And then I will show you that if such a neutrino actually exists, it can play important role in astrophysics and cosmology. So this I will just mention, and perhaps in the end of the course, when you have some special talks on astrophysics and cosmology, we will go into this part. But right now, let's only deal with oscillation. So let's look at what a short baseline is. So everyone remembers that if you have let's say 3 neutrinos, and if you want to calculate probability of conversion from mu alpha to mu beta, okay, it's given by this 1 or 0. This is the CP conserving term. Plus there is a term which is known as imaginary part of this bracket, which is CP value. For clarity, let's first deal with situations where there is no equivalence. So let's forget about this third term for the moment. Okay. Actually, the final analysis we have to bring it in, but right now let's forget about it. So, now, if we will go to a specific class of experiments where only one data is very significant. Okay. So, see, this is size to delta GI. Now, delta GI can have different values depending on what you want to do. There was standard formalism. You have delta 3.1, delta 3.2, and delta 2.1. And we know that delta 2.1 is much more than delta 3. There can be certain situations where, for example, only delta 3.2 and delta 3.1 are significant, and delta 2.1 is very small. For example, let's say we go to a situation that delta is delta m square L by 4. So we choose our L and E so that delta 2.1 is very small. Let's say delta 2.1 is 10 power minus 2. Then sine square of delta 2.1 could become 10 power minus 4. And which means we don't really need to care about it. At the current level of accuracy, we cannot go to P alpha beta more accurate than let's say 1%. We don't even think about such things. Okay. Therefore, if we are in a situation where delta 2.1 is very small, 10 power minus 2, then one can just forget it. So let's start to go to those experiments, for example, where delta 3 1 is increasing. So delta 3 1 is 1 of the. If delta 3 1 is 1, how much is going to be delta 2 1? So if delta 3 1 is of the order of 1, what is delta 2 1? It's about 1 by 30, factor of 30. So it's 1 by 30. This means that sine of delta 2 1 is 1 by 30, which means that sine squared of delta 2 1 is nearly 10 power minus 3. So therefore, if we have experiments where delta 3 1 is of the order of 1, then this term is negligible. So these are what are generally called as short baseline experiments. So they have enough baseline that you can look at oscillations that happen due to delta 3 1, which is like delta atmosphere. But the baseline is too small to see oscillations due to delta solar. So oscillations exist, but you won't be able to see just because they are very weak. So we will try to go to such experiments and let's see what happens. We will talk about more general things, where there may be many neutrinos. Okay. Even if there are many neutrinos, this formula will not change because there is going to be a mixing matrix U, and these U will appear in the same combination to give you this bracket. Because remember, nowhere in this formula do we say that number of neutrinos is equal to 2 or 3 or 4 or 5. This is a very general formula. Any number of. So let's go to, so among these deltas, one of them is the largest. Okay. Normal case, delta 3 1 was the largest. So now, we look at those experiments where the largest delta is of the order of 1. And all the others are negligible. Okay, like 1 by 30. So now what happens? Now, we will be able to write down our P, let's say alpha, probability of survival, as 1 minus something times sine square delta. Because see, either your delta iji will be equal to delta, which is the maximum one, or it will be negligible, so 0. So it's possible that you have many terms here. Okay, but all the terms which are non-zero will have a factor of sine square delta. So therefore, I can always write down my survival probability as 1 minus something, that something is whatever is this part times sine square delta. Similarly, if I want to find the probability of convergence, it will be some number times sine square delta. Whatever this is, we call that sine square to theta equal. It will be some number. You know the number is going to be between 0 and 1. Therefore, we can call it sine square theta. Because then now it looks exactly like 2 neutrino oscillations. So even though we had many neutrinos, 3 or 4 or 5 or 15, the probability of survival and convergence will always look like 2 neutrino convergence. So sine square 2 theta times sine square delta and 1 minus.
So sine square theta and theta in first equation, theta in second equation. Theta f.
Theta effective.
Both are different.
Absolutely. I haven't shown them to be the same, but actually
It should be different.
In principle they can be different.
Under that approximation, I don't think different.
They can be different. So for example, this alpha, mu alpha, may go to 2 different neutrinos. And then one of them, it will go with probability something, other with
Yeah, but once you make the approximation that all of them are either delta or 0, then I think even if it is the can go to two things if you go to the same.
No. So let me give you an example. So, let's take the example of 3 neutrinos. So let's say our scheme of neutrinos is like this. And I go to a situation where only this is significant. But now we have a term which is delta 3(1) and a term which is delta 3. Both of which are significant. And now if I want to calculate the probability of, let's say, difficult to say this. Okay, so forget about mass. So let's say I produce something here in mu 3. Then part of which will go into 2, and part of it will go into 1. Which part will actually depend on some mixing of the theta 1, 2. So it's quite possible that I get, although data is the same, I will be getting mu 2 with a different probability and mu 1 with a different one. So maybe I'll concoct an example in the assignment which actually will be. But for example, okay, there is one simple way to see this. Now note that the sum of these two is equal to 1. This and this is 1. Therefore, if your alpha is going to 2 different neutrinos, it is very clear that this factor is going to be different. And sum of the 2 is going to be equal to psi square. So, yeah, that's perhaps a simple argument to show that it's possible. Okay, so this is the situation, and this is normally what is called a short baseline experiment. Because most of them operate in this regime where only one delta experiment, which is the largest. Okay, so then we have to look at how the contours of sin square 2 theta and sin square delta look like. So what do we do? What this means is we produce lots of mu alpha. Okay, we try to see how many mu beta are produced. And we know that number of mu beta produced are going to be something like this. Let's say we measure this and we find it to be equal to 0.5. Let's say 0.2, 0.5. So what you want to see, so let me make so P alpha beta, this was found to be equal to 0.2. So let's see. So now you have to see what this will look like on a plot which has delta n square, this axis, and sin square 2 delta x. So we know what this looks like. So this should be sin square 2 theta effective times sin square of delta. So let me just say delta. It is easier to just talk about it. So sin square of delta. So what will this value look like? If I want to plot contour of P alpha beta equal to 0.2. So firstly, so this is 0.2. This would mean that sin square of 2 theta effective has to be more than 0.2. So they will like this because it gets multiplied by sin square delta. So sin square 2 theta effective. Here it's 0.2. Whatever contour we get has to lie on this side of it. So the whole line will lie on the right hand side of this contour. Now, look at the following. If delta is very small, okay, so let's say sin square delta is sin square delta should also be greater than 1. Do you agree with this? this because there is sin square theta. So therefore, if delta is very small, this constraint cannot be obeyed. So for very small delta, this offers no constraint at all. You start getting constraints only from some point, this point for example, where sin square theta is of the point. And now you can try to see, in fact maybe I should use the homework point. So you get contours and two points. It's very similar to what we got for the atmospheric Neutrino or for the Minus, which is very similar, right? So all the experiments like K2K and Minus, they're very similar. Right? Basically, the solar neutrinos parameter don't play a part. You have got delta 3-1, and therefore the contours you got look like this. So I think perhaps when you quantify yourself, you understand it. Another thing is that when you go to higher and higher values of delta, this is periodic. So you can actually get contours here. You have periodicity in this. So this means that all these lines, so if you are on these lines, then your value of P alpha beta can be equal to 0. So let me go one more step further because this is very boring. What I will do is on the x-axis, I will try to see log of J. Log delta only means that to the higher scales get complex. So which basically means you get complex like this. And so what do you think will happen at very large deltas? That's delta much larger than so it will be almost continuous, but what will be its amplitude? So you write down that P alpha beta is sin square 2 theta effective and sin square theta. So what happens at large delta? So remember delta is delta m square times L by 4e. So what effects come into play when you go to very large delta? Which is like going to very large lengths. Decoherence starts coming in.
So you get average.
So you get some average value. So if you go to very high delta, you will get average value. Therefore, this P alpha beta is going to be sin square 2 theta effective times the average of sin square delta, which is so at large delta m square, you will come to you get average. So in fact, these fast oscillations, it's as if they are getting averaged out and you get a line. So in reality, you will get line like this. You start oscillating and you will get something like this. This is again because at some point of time you stop being able to resolve between energies. Therefore, what you will get is this sin square 2 effective hence I have a log delta. You see that at very large values you will get a line like this, then they start oscillating. I am not trying realistic function, but very low value. So this means that one measurement will tell you that you lie along this line. If you find that your answer is 0, there is no conversion, then this means that you have to lie on this side of it. So this means no convergence. Because this is P alpha beta, which is much smaller. On this side, it means convergence. So if you don't see any neutrino convergence, you say that I ruled out this parameters. So this concept is. So the aim of short baseline experiments was twofold. Okay, these experiments started much before we established our values of delta and atmospheric pressure. So the idea was to try at all possible values of L and D and see where you strike both. So if you actually see oscillations, if you mean that you will say that the region that looks like this is an allowed region. If you don't see oscillations, you will say that region on the right hand side of this is ruled. So these are the two things that short baseline can do. It can either give you a region like this as an allowed region, again it will say allowed, or it will say that this is what. This is what you will get if you just make a simple experiment. One more important concept of this was the following. See, what we saw here was that there is some value of delta below which experiment tells you nothing. So this was we saw it here, right? So if sin square delta is less than 0.2 here, okay, it tells you nothing at all. So therefore, you will only be sensitive to the values of delta above a certain. So let me get more. So since your P alpha beta is equal to sin square sin square delta, delta has to be significant of the order of 1. If it is 0.1, your probability becomes n to minus 2 and perhaps you only going to see. So for an experiment to be sensitive to some value of delta n square, your delta should be of the order of 1. So for example, if you look at atmospheric neutrinos, our energy is about 1 GeV.
But if you have a large enough flux, then that becomes
No, we don't have that. So we are talking about experiments where your accuracy is of the order of 1%. Not
So what sort of sources will be? What sort of sources?
I will come to this. So what kind of sources, and in fact, even atmospheric neutrinos are such a source. Because you have energy of 1 GeV, then length is say 10⁻³ kilometers, 1000 kilometers, which tells you that delta n square should be greater than 10⁻³ electron volts. Because you remember this, right? So this is delta 1.27 times delta n square, v square, L in kilometers divided by E in G. So for atmospheric neutrinos, delta n square should be greater than about 10⁻³ electron volts. This is the reason why solar neutrinos, the solar parameters don't play a part in this. Although solar oscillations do occur, even in atmospheric neutrinos, you don't see them. Just because the L and E are such that you are not sensitive to 10⁻⁴ electron volts. Delta n square solar is less than. Then we can look at reactor neutrinos. Reactor neutrinos have energies of the order of 1 MeV and length is of the order of 1 kilometer. So, which again means that this is of the order of 10⁻⁻3. So, delta should be greater than 10⁻⁻3. Because reactor neutrinos will again be sensitive only to delta to atmosphere, and not this one. Now, let's go to long baseline experiments. Here energies are like 1 to 10 GeV. Length is about 10,000 to 10,000 kilometers. And again, this means that delta n square should be more than 10 power minus 3 vector. This L by E actually cancels. 10 GeV and 4 kilometers is 10 power minus 3. So again, in long distance experiments, to first order, we do not see the solar oscillations. We have to go to accuracy which is more than 1% if you want to see solar oscillations. And now for the short distance experiments, which are usually accelerated experiments, you start with energies of the order of about 10 to 100 MeV. Then you have reactor, you go about 1 kilometer away from the source, so it is 1 kilometer. And this means that you are sensitive delta n square about 10 power minus 2, 10 power minus 1 electron volts, so much larger. With the knowledge that we have now, we expect that nothing will be seen because it is not sensitive to solar delta n square, it is not sensitive to atmospheric delta n square. We know it now, but we did not know it 15 or 30 years ago. Therefore, we tried all such combinations to see what it is. So, what did it give us? So, this plot is looks very complicated. It basically is most of the experiments that people have done till now, and what the answers look like in the approximation of one mass square, single mass square dominance. This is 1 delta n square. So, this part is familiar. This is the solar part, and this part is the high delta n square. So let me expand this. So let me just cut it here. So then we will cut the lower part and upper part separate. So that will be slightly less. You have seen this solar figure in some form. Right? So this was the large mixing angle solution. This is small mixing angle. This is low. This was vacuum. And you saw that this survived. Solar revolving neutral. This is tan square theta, right? This actually is not sin square 2 theta, but tan square. Whatever is your sin square 2 theta, you cannot distinguish between angles less than 45 and more than 45. So it's good to put tan square theta. That can distinguish. So now here, if you go up, you see this sort of bluish and yellow bands. They stand for superconductor atmospheric neutrino. Again, you know that a solution is a 2 neutrino solution almost, and angle is almost 45 degrees. You see that this actually lies at tan square theta is equal to 1. Theta is equal to 45 degrees. Initially, this experiment show about which we talked earlier. Show was one of these short distance experiments, and Show did not see anything. Show said that neutrinos don't seem possible. So you get this bounce on by Show. So you see this contour. Contour goes like this, comes back, and as it goes up, it will again settle up. Similarly, this was this K2 experiment, which also we have seen earlier. Again, the contour will go and loop. So this is a universal shape to all contours. What will matter is at what delta n square electron sensitivity. That depends on the actual experiment. So let's go to high delta n. Okay, so again, this is tan square theta. This is 1. This is delta n. So this is the Show contours. They go like this, oscillate a bit, and then becomes straight line as they go on. Okay. It also happens on this side because sin square 2 theta is symmetric. You will also see another experiments which is called as Dighe, this green line. Again, oscillating part here and becomes straight line as you go on. Then there is this experiment called Nomad, where you will see a line that goes like this and settles apart. There is also this Chorus, whose peak is somewhere here, and if I really go high, it will again become straight. So shape is universal. What differs in these experiments is the value of L and E that they have. Depending on the value of E and L that they have, the sensitivity changes. So Nomad, for example, can rule out a region which is above it. So nomad can say nothing about this region. Whereas show will say something about this region. It will say that the region to the right of this red line is ruled. Another experiment called CDHSW. Let's not go into that. You also see this thing called Carmen 2, which is also something that goes to a peak and then oscillates it. So all these experiments were done in parallel with different levels of N and E and had different constraints. Essentially, they told us that whatever lies to the right of these lines is going to be ruled. So they rule out some value of tan square theta, but ruling out depends on the value of delta tan square. Is it okay? So till now I only talked about those that rule out. Okay? But then you see this band over here, this bluish and yellow band, which says minimum here and LSND. So let's see what that means. So LSND was an experiment, this liquid scintillation neutrino detector, where you created a mu bar beam and mu neutrinos. Energy line range was like maybe about 10 MeV to 100 MeV. So you create mu bar and you try to look at mu. So looking at all the other experiments, it will appear that, for example, let's take the example of this nomad. So nomad rules out this area completely. Or if you look at this bougie, this will rule out this region completely. Therefore, one would expect that you should not see any excess. If you start with the mu bar, almost one of the mu bar should convert to mu bar, and then we are safe. Maybe one thing would be look at this expression. So remember, this was the 3 neutrino probability expression. And we had this PE mu, which depended on the value of sine squared 2 theta 1 3. So if sine squared 2 theta 1 3 was very, very small, then this term would vanish, this would vanish, this would vanish. And this term is alpha squared, which is 10 power minus 3, so that's very small anyway, so forget it. So if you had sine squared theta 1 3 as, let's say, 0, the value of P mu would be equal to 0. So if you see P mu E is actually, so P mu E is just the same as P mu by changing delta C. That doesn't matter. So even value of P mu E would be equal to 0 if theta 1 3 or 0. So when people had seen all these experiments, all the short baseline ones, which always gave negative results, which always said that if you start with a mu, look at mu bar, you will not see any response. People expected that maybe theta 1 3 would be 0, and then that would be it. What LSND did was it actually was able to see an axis. So these black points are data points. The background that we expect is this red plus green. So now you can see that the data points are much above the background, which is red plus green. So in fact, this blue colored region is the region with oscillations. Okay, with the base. So
What
when
parameters?
sorry,
Blue is with what parameters?
with the basic parameters. So I will come to what is parameters. So I think one of them is mu, one is mu bar. Okay. So this is mu bar and mu bar oscillations, mainly. And they actually found an excess, and you see that excess is much above the background. So this is almost 90 events. So it's more than 3 sigma. In fact, perhaps even more than 4 sigma. So this is a significant sigma. Not only that, if you try to plot excess number of events with L over E, because in L over E you should see nice oscillations. And you see here that you actually can imagine that it actually goes up like this and comes back down like this. So the kind of event that you see actually do fit oscillation hypothesis. Probability of oscillation is 0.26 plus minus 0.06. So again, this is more than 3 sigma. So it's a well established result.
Third number is the error in the error.
Third number is systematical. The second is statistical, third is systematical. So normally you add them in quadrature. If you add them in 6 and 4 in quadrature, I think you will get something like 7 or 8. So this is more than 3 sigma. So this is fine, not too bad. Except that the delta m square for which you got a fit was this 0.2 to 10 electron volts. See, LSND was not designed to look for delta m square of 10 power minus 3. Okay, because A and E are not compatible. It was sensitive only to delta m square more than 10 power minus 2, 10 power minus 1. So not surprising that you got delta m square equal to of the order of 1 electron. So now, if we trust these experiments, it basically tells us that this region is allowed. So we talked some time back, right? That if you actually see something, you get allowed region that look like this, of this one. So some peak, you go up and you go first. So LSND told people that actually you get a curve, allowed curve that looks like this. Now let's see what the other constraints. This nomad experiment, which has this line, had ruled out this region. So this was still okay. Then there was this Dighe experiment, which had ruled out this region. And then there was the Carmen experiment, which actually happened slightly after LSND, which ruled out anything to the right of this line. So nomad took out this region, Dighe took out this region, Dighe took out this region, and Carmen took out this region. But still we had this small sliver of LSND. So in some sense, most part of the region which was given by LSND actually was in contradiction with some other experiments. Okay. So with nomad, Dighe and Carmen. So question now was what to do here. One possibility is that maybe there is some problem with LSND. Second possibility was actually this small region is allowed, tells you exactly what the parameters. So let's first start assuming that whatever LSND is doing is correct, which would mean that we have this region. So if you look at this region, this corresponds to delta n square of the order of, as I said, 0.2 to about 10. So delta n square is of the order of 1 electron, plus minus factor of 5. And sine square to theta is about 10 power minus 3 to 10 power minus 1. So sine square to theta of the order of 10 power minus 2 with some factor of 5 or something. So as far as only looking at LSND is concerned, there was no problem. It's an experiment. It gave you oscillations, it gave you some good numbers, and that's it. So just like you observe something in solar atmosphere, you observe something in LSND. So at this point, there is not a problem. The problem occurs when you try to look at it in conjunction with what we know from the solar atmospheric experiments. So solar experiments have told us that delta n square is some 8 times 10 power minus 5 electron volt square. The atmospheric ones have told us that it's of the order 10 power minus 3. LSND was of the order of 1, so at least more than 0.2 electron volts. Now if you look at this, you will see that if you have 3 neutrinos, it's not possible to fit all these 3 data. You cannot have 1 10 times 10 to the minus 5, 1 of 10 to the minus 3, and third of 0.1. It's completely impossible. So therefore, one of these must be wrong. In fact, about 10 years ago, a lot of people were trying to say, okay, fine, so maybe atmospheric is wrong, let's try to combine solar and LSND to form a 3 neutrino picture. Then there are some other people who said, okay, maybe solar is not do oscillations, let's combine atmospheric and LSND and make a combined 3 neutrino picture. And people then had to do different mechanisms for solar. So people said, okay, maybe solar doesn't happen because of oscillation, it happens because of something else. So people had many such different models about 10 years ago. However, one thing was sure that just because of these delta m squares, you cannot have only 3 neutrinos. So therefore, you have to have 4 neutrinos. This is not compulsory. If you want to explain all these 3, you need 4 neutrinos. With 4 in principle, this is possible as far as delta m square is concerned. If you have one solar delta m square, one atmospheric, and one LSN, that's okay. That's what it is. So now we have to add a 4th neutrino and see what we get out of it. So first question to ask would be, is it a sign of a 4th generation? Of course, we have 3 generations. We know that there is no other reason why generation should be equal to 3. Okay. And therefore, you could have a 4th generation. Have people seen this thought before? Everyone should see this thought and play to it. So this is perhaps the most accurate measurements of harmony. So this is the plot made at this large electron position collider at CERN. This collided E plus and E minus at Z resonance. Z mass was 90 is 90 GeV. So you collide E plus E minus at 90 GeV. So you produce Z. Z always decays to pair of fermion. So it decays to, let's say, E plus E minus, mu plus mu minus, tau plus tau minus. Also to clocks, UU bar, DD bar, BB bar, CC bar, SS bar. Not TT bar because T is very heavy. Okay. And the rate at which it decays tells you about the line shape of Z. If you just look at a cross section of this process, you will get a nice peak around 91 G, which is the mass of Z. These 4 are the 4 experiments at length. This is the combined measurement. Okay. Now, of course, this Z will also go to mu bar, mu bar, mu tau bar. And each time it goes to more number of particles, its width increases. So width increases would mean if you normalize it well, the peak actually goes down as you have more and more number. So if you have 2 neutrinos, you get this red curve on top. With 3, you will get a green curve, and with 4, you will get this curve. So this is perfectly well established standard electrometry. Now look at the data points. You will see that the data points lie almost exactly on this 3 neutrino. Note that the error bars have been multiplied by a factor of 10. So the error bars actually are 10 times smaller. Therefore, to very, very high accuracy, we know that number of neutrinos is 3. So in fact, if you do a fit from this measurement, you will get a number that looks like this. 2.985 plus minus 0.008. So we know that number of neutrinos is 3 up to this accuracy. Well, there is some caveat. Firstly, these should be neutrinos which are lighter than Z. Of course, we can have a very heavy neutrino which is heavier than Z, and Z cannot decay to these neutrinos. That's always possible. So we still have a scenario of very heavy neutrino in 4 generations still allowed. That's possible. However, we are looking at delta M square of 1 electron volts. We are looking at light neutrino. That's not our concern. So this neutrino, therefore, since it's light neutrino, it cannot interact with Z. Because if it interacted with Z, then you would get a curve that looks like a 4 neutrino curve. So therefore, this 4 neutrino cannot be a 4th generation neutrino. People agree with this? No, that's contrary. No, so because we know that this neutrino has a mass of the order of 1 electron volts. So we are trying to look at the neutrino which will explain this LSND anomaly. LSND anomaly tells you that delta M square is about 1 electron volts. But we know that other neutrinos mass is less than 2 electron volts. See, we have this beta decay experiment which told us that the mass is less than 2 electron volts of all the other neutrinos. So therefore, this cannot be whatever 900 GeV. So it's possible that there is a 4th generation neutrino, which is heavier than Z, but that is not LSND neutrino. Okay, so we are trying to look at LSND. Okay. So therefore, this neutrino is not a 4th generation neutrino. So it's what is called a sterile neutrino. Okay. Sterile simply means it does not have electric interactions. Does not interact with W, does not interact with Z. That's what it strictly means. I mean, you may even wonder why to call it neutrino. Neutrino usually is, you have electron neutrino, muon neutrino. There's no reason. It's a good name. It's a good name for a fermion which is chargeless. That's why it's called neutrino. That's it. There's no other reason.
Then how it is generated? Does it participate in all 4 interactions?
So there must be some interaction beyond these 4 where it participates. So only reason we call it sterile is that it doesn't interact with W or Z or kappa. That's all it means. Okay. It does not have electrophilic interaction. Sterile doesn't mean does not interact with anything else. Okay. It's possible that there are some other gauge bosons that we have not yet found. It may be very, very heavy. It interacts with them. There's no problem. Okay. So there's no such concept. So indeed it can have interaction beyond the standard model. This is very important. Okay. So no one rules this out. It can have no interactions. It can have very large coupling constants there. Okay, it may even be of the order of 1. It's perfectly okay. Because the constraint comes from decay of Z. So as long as Z doesn't give you problems, you are safe. And because of those interactions, it can mix with light neutrino. So it's possible that there is some interaction which is new sterile and some other boson. Well, we don't know anything about new physics. So it's possible that this interaction exists. So right now we don't need to know what the details of this interaction. Most importantly, as some misconception, this is not right-handed partner activity. So you might think that this is we have new L left-handed. Can this be a new R? Okay. The answer is no. This is not right-handed partner. That's a completely different one. The right-handed partner of active neutrino is also called as sterile neutrino. It's called as mu R. It doesn't interact with W or Z, so in that sense it is correct. However, if you want delta M square of 1 electron volt square, this is not it. Usually right-handed neutrinos have a mass of the order of some 10 power 12 GeV or so. Okay. So this is not it. Okay. Either neutrinos will come to this, but for those who know, either neutrinos have only Dirac mass, in which case the mass of mu R the same as mass of mu L, because it's like electron. Or they have Majorana masses, in which case mu R has a mass of 10 power 12 GeV. None of these is this LSND neutrino. So this is all we know about this. This is light sterile. So now what we try to do is we try to put this neutrino into our model and see what happens. Because our next job is to see how we can constrain it. We want to find what its mass is. We want to find what its mixing angles are and so on. Let's try to do that. So let's accept that we want to explain LSND. Therefore, we need to have this sterile neutrino. And once we have it, we have to find out how it mixes. So this is what we try to see. So once you put in this extra neutrino, what will the neutrino masses look like? So remember earlier we had these two hierarchies, normal and inverted, because we did not know how to put in this solar, atmospheric and LSND. Sorry, solar and atmospheric. Now that we have put LSND, we have many more combinations. Okay. So you will see here, no? So atmospheric, solar and LSND can be put one over the other in many different ways. These four ways are the ones in which LSND neutrino is far away and atmospheric and solar is very close together, just like what we had earlier. These are called 2+2 cases where actually atmospheric and solar are not close together but far away. Okay, but this is a historical thing. Now we don't talk about this. But of course, these two are the main scenarios. In principle, you would like to distinguish between these two. Now we are going to do 4x4 framework. It's 4 neutrino.
What is the significance of 3 plus 1 and 3 plus 2?
Yeah. So you see in these four scenarios, the extra neutrino is far away from this. Okay. Therefore, one can say that this scenario reduces to the standard 3 neutrino scenario in the limit that this neutrino doesn't interact at all. Okay. So in these four, that is possible. You can say that this angle is what determines the mixing of sterile neutrino. These scenarios are ones where that doesn't happen. So in no limit can you go to our standard 3 neutrino framework. Because atmospheric is here, solar is here. So this scenario therefore will conflict with everything. So it's very easy to do out 2+2. People have to read out very easy. This was slightly hard to do out because this is more quantitative. You have to figure out what is the angle of mixing of this LSND neutrino. So we will come to how to do it. See what this means is the following. This means that solar neutrino oscillations happen in some parameter space. Atmospheric happens somewhere else. Therefore, if atmospheric happens between mu and tau cannot take part in solar neutrino, which is bad. Therefore, it's easy to do. Right? If you can come up with more mass orderings, I'll be happy. I suspect that there are basically these 6. So now we are going to 4x4 case. So remember 3x3, we had done this counting. So we had this unitary matrix U. So U 3x3 had 9 parameters. So 18 parameters minus 9 constraints due to unitarity. And that gave us 9 parameters. 3x3 matrix has 3 mixing angles. So this was 3 angles, 6. Now we are 4x4. So this is going to have 16 times 2, so 32 angles, minus 16 conditions, so 16 parameters. So 4x4 mixing, so 6 mixing angles, 6 angles, and remaining are going to be phases, 10 phases. So if you do it complete analysis, that's much more valuable than 3x3. You won't do this. It's just to assign the hard thing that we can do. Again, if you want to parameterize this matrix, there are many ways. Okay. However, this was a way which is similar to what we did earlier. So I just want to put it in front of you. We won't do anything with this right now. So again, you have 4 flavor phases. Chi1, Chi2, Chi3, Chi4. 6 rotations. 1, 4, 3, 4, 2, 4, 2, 3, 1, 3, and 1, 2. And 3 Majorana, 5 and 5. So if you want to do a complete analysis, you have to use all these parameters. Oscillations means that actually these phase matrices won't count, but you will still have 6 rotations. And these, remember, are now not 3x3 matrices, but 4x4 matrices. So those deltas, the different earlier I guess it was delta C. Yeah, there's only one delta. Yeah. Now we have 1, 2, and 3 segments. So there are 3 sequential. So if they get one Yaskov invariant, independent of sign delta. Now you will have 3 different. So things become messy. You have to go to complete analysis. Unless it is other different. So let's try to constrain this sterile. So first thing to do, people were rather upset that you have to do this 4 to 2. That's not very nice, right? And all the experiments see nothing and this will do something. So what they did is they considered an experiment which was almost similar to LSND. So this was called mini boon. Energy here is around 1 GeV, so 200 to 3000 GeV. I'm sorry, 200 to 3000 MeV. Okay, the distance was about 1 kilometer. So sensitive to the same region. In this, the green region stands for no oscillation hypothesis. And blue ones stand for oscillation hypothesis. You can't see it very well from here, but no, maybe you can. That the oscillation hypothesis is actually much worse. Null hypothesis fits much better. So, unless you do chi-square, you can't say it. So, ideally, to say things, you have to calculate the chi-square and see what comes out. Okay. But take it from me that the chi-square for null hypothesis was much smaller than that for something with 3 plus 1. So therefore, this experiment also said that LSND perhaps is not very good, not consistent. So this is what happens when I try to constrain this sterile neutrino from all the experiments that I talked about till now. These are all so-called appearance experiments. Okay, in the sense you have mu beam, you look at mu e. Okay, so mu e appears. So some are the ones that you have seen. You have seen this nomad, which are these curves. Then you had this, you looked at this Carmen before. Okay, Carmen gave you curves that look like this. The other experiment which had to do with mini-boon, which was a very weak constraint. But the LSND plus mini-boon with neutrinos plus mini-boon with mu bar, okay, again ruled out many things, but gave you this small sliver. So LSND, sorry, mini-boon still ruled out a lot of parameter space of mini-boon. Okay. I'm sorry. Mini-boon did rule out a lot of parameter space of LSND, but still, of course, when you combine things, you will always get a best fit. Okay. However, see that the best fit point is now here. The chi-square is also rather high, and the regions above are ruled out by other experiments. So, it is said in general, folklore is that mini-boon ruled out LSND. Mini-boon didn't rule out LSND. Mini-boon reduced LSND to a much smaller region. This is the main thing that it is that mini-boon. However, it's not just that. Sterile neutrino is going to affect everything. It's going to affect solar neutrino oscillations. Because now your Sudbury experiment indicated that most mu go to mu and mu tau. So your constraints on sterile neutrino, mixing between mu e and us. So you have some constraints. Then you look at atmospheric neutrinos, you get something due to our older framework. Okay. Plus, you get this sin square 2 theta times 1/2 because of the averaging, sin square delta averaging. So you get this extra contribution. And you have, therefore, you are bound from atmospheric experiments on this mu to mu sterile mix. Then your reactor experiments. So we had this Kamland experiment, which was mu e to something else, okay. And we saw that that cannot be mu s. Then we had you look at minos, you produce mu mu's, and look at disappearance. That will be constraints on the mu sterile mix. Okay, so these two are constraints. Then we have got this show experiment, okay, which was mu to mu e, which means you get constraints on mu sterile mixing as well as mu sterile mixing, because you have to go through the first sterile and then mu. So all these experiments are there. In fact, combining them, they have much more data than only minimum experiment. So now if you add percent to everything, that is this, then you get something like this. So these are all called as SBL experiment, short baseline. But short baseline includes atmospheric, Kamland, Minos, K2K, everything. And then you get contours that look like this. Everything to the right of this is ruled out. Okay. So therefore, you see that the region that is required by LSND plus minimum is ruled out almost completely if you have all the data that we have. So once you include disappearance experiment, almost all the region that was integrated by LSND is now ruled out. So remember, LSND is the only one which had seen oscillations. Minimum did not see any oscillations. None of the other experiments saw any oscillations. However, fitting with LSND was giving you some allowed region, but once you took the help of all the other experiments, a combined fit ruled out LSND region to a very, very large extent. So status now is that one may safely say that LSND is ruled out. So people suspect that LSND experiment did perhaps some systematic error they didn't understand. So the experiment now is now closed, so you can't go back and see what it is. However, now most people tend to believe that there was some problem in LSND experiment. So essentially you ignore it. Okay. People tried many things. People said, okay, maybe one sterile doesn't work. Maybe we get two sterile neutrinos. So two sterile neutrinos called nu4 and nu5. Then you get parameter space of delta m square 4-1, delta m square 5-1. Then you said, okay, if it's not CP conserving, it's CP violating. So you want to try CP violation. So you put in all the imaginary parts of that. Okay. If you do that, of course, you do everything, you always get a best fit point. So they will always the best fit point. You get a best fit point here. Okay, this 3 plus 2 CP violating case. Okay, with everything. That point is here. Now you see this point, this has delta m square 4-1 of 1 electron volt square and delta m square 5-1 of some 10 page electron volts. So what does this mean? This means that you need two sterile neutrinos which are of the order of electron volt masses. One of them may be 5 electron volt, something like that. And then cosmology tells you that you can't have neutrinos heavier than, let's say, 2 electrons. So people do a lot of attempts to salvage the situation of LSND, but till now they are essentially free. Okay. So at this point, therefore, the best practical strategy is to ignore LSND and work with you. It's good to know that we should be ignoring. The question is then, why did I tell you all these things? Because I tell you that sterile neutrinos may exist, then I tell you that they are ruled out. Okay, so the reason for this is people have hope. People have hope that there will be some new physics because people like new physics, right? It actually comes in handy in certain cases. So I just mentioned a few cases where it's useful. It's useful in astronomy and cosmology, for example. For example, in stars, very heavy stars, you have nucleosynthesis. You produce very heavy elements. Now see, heavy elements means more number of neutrons. As you go to heavier elements, you have a higher number of neutrons and protons. So in the star, therefore, you will need to get more and more neutrons together. If there are electron neutrinos, they will kill you. Because if your nuis, they interact with neutrons, make electron and proton. So whenever a nucleus starts forming, the nuis will come, interact, it will break the nucleus. So it won't be able to form. So nuis are bad for making heavy. Now, let's say you have.
It might be also true that nu is oscillated to nu tau.
Yeah.
Then also.
But now what happens? This is happening at very large densities, where all the neutrinos are trapped. So density is so large that nuis are trapped. even nu's are trapped because even they interact. Now if nu is oscillate to nu sterile don't interact with anything, with matter. So they are not trapped, they just go out. Okay. So now what can happen is nu is convert to nu sterile and they just go out. Okay. And then you don't have nu is, so you have smaller number of nu is, then you can make more number of neutrons. And then that works. However, that works only if delta square is about 10 to 100 electron volts. So not the LSND one, but slightly heavier. Another thing that it can work is for supernova explosions. Okay. So firstly, if you convert nu is to nu sterile, okay, nu steriles go out very fast. Okay. So which means the energy of collapse is carried out very efficiently. So the star cools very fast. So this is going to affect the way you explode the star. We'll talk about this sometime in the later course and give a special talk about supernova. And also this means that now that there is no control over in which direction this nu sterile will go out, okay, there are large asymmetries in the emission of the neutrinos. What it would mean is that the star which is inside this will now start moving with very high speeds. There is large asymmetry. Okay. Such a phenomenon is observed, what we call as pulsars. They move with very large velocities compared with other stars. So this is something else. They move with speeds of the order of maybe 2 or 3 times the speeds of normal stars. People expect that maybe that's because of some asymmetry that is. But again, this is something that we will look at in the later. In cosmology, it just mentioned these three. So if you have got KEV neutrinos, they are good for dark matter. In fact, these KEV neutrinos also can help you in making supermassive black holes. We know that at the centers of all galaxies, we have supermassive black holes. If we actually have sterile neutrinos, which are KEV, you can help them. They are not required, but they help. So it's good. And there are some models. This is called the new universe standard model. They try to explain things like baryon asymmetry, repulsion and so on. That involves sterile neutrinos. So therefore, people like sterile neutrinos, even if they are not required for oscillations. So this is my last answer. So we don't have a last word of sterile neutrinos yet. Electron volt neutrinos are not required for explaining the oscillation data, but they are not ruled out either. LSND space is ruled out. But of course, if you get very, very small mixing angle, they are still possible. So not required, but not ruled out. Next, they can help in some astrophysical phenomena like making of heavy elements, giving speed to pulsars and so on. But then we need delta square of the order of 10 electron volts. And then you can have KEV neutrinos, which can stay in cosmology or structure formation. So this is the bottom line essentially. Electron volts not required. 10 electron volts square, good for astrophysics.